So in section 6.2, we're going to learn how to use the substitution method to solve a system of linear equations. So if we recall the following from the last section. So a system of equations is just a set of more than one equation. And a solution to that system will be the values of the variables that make all of the equations in the system true. And to solve such a system involves finding the values that make all of the equations in the system true simultaneously. So in the last section, we learned how to solve a system of linear equations by looking at graphs and tables. And that was a good place to start, where we graphed them and we were looking for their intersection point. But what if we had a solution like 2.34, 4.154, if our intersection point did not occur at some nice integer value like 2, 4? Okay, the graphing method gives us a nice visual way of seeing the solution to the system. However, many times the coordinates for the solutions are not going to be nice integer values. So in this case, we need another method. So to solve a system of equations in two variables, we're trying to find an x-coordinate and a y-coordinate that make both equations true. So the x value in one equation must be the same as the x value in the other equation at that intersection point if it exists. So this gives us another way to solve a system of equations using the substitution method. So given the following system, 2x plus y equals 12, negative 3x plus 2y equals 6, we're going to first find an approximate solution using the method that we've already learned, which was the graphing method. So the first thing that we should notice about these equations is that they are linear equations. Every term is either an x term, a y term, or a constant term. And in our other equation, again, we only have x terms, y terms, and constant terms. We don't have like x squared terms or xy terms in here that would make the graph look somehow different. So in this case, every equation has just x terms, y terms, and constant terms. So we have linear equations, which means their graphs will be lines. And to graph a line, we only need 2 points. Okay, more points is nice just to do a double check on our math, but we only need 2 points to determine the graph of a line. So 2 points that are easy to find are the intercepts, where we just plug in 0 for x or 0 for y. It kind of makes the mental math nice. So for the y-intercept, we're going to plug in a value for x equal to 0 and find out what that y-coordinate has to be. So if we plug in x equals 0, we're going to get 2 times 0 is 0, plus y. So over here we just have y equals 12. So the point 0, 12 makes this equation true. If we plug it in, we get 0 plus 12 equals 12, which is true. So these are values of the variable that make the equation true. Therefore, this ordered pair is a solution and must be on the graph of this equation. Now to find the x-intercept, we want to find the x value of x when all the other variables are 0. So if we plug in y equals 0, we're going to get 2 times x equals 12. And 2 times what number gives us 12 would be 6. So again, if we plug this in, we get 2 times 6 is 12 plus 0, which is 12. 12 equals 12 is a true statement. So 6, 0 is an ordered pair that is a solution to this equation. Therefore, it also has to be on the graph of this equation. So if we plot these 2 points, we've got a point up here at 12 on the y-axis, goes off our scale here just a little bit, and we have a point on the x-axis at 6. And if we look at our slope, okay, so our y-coordinates went from 12 to 0, so they dropped 12. And our x-coordinates went from 0 to 6, so they went up 6. So our unit ratio here, we're going to go down 2 every time we go to the right 1. So down 2 to the right 1, down 2 to the right 1, and we can keep going. And we should end up with our other point by our other point there, which we do, but I'm just going to keep going. So we've got some more points to connect. So now if we connect those points, and we do see our graph is a line, like we said when we looked at our terms. Oops. All right, so we get a graph that looks like this. Okay, so that was our first equation. All right, so now if we do the same thing with our second equation, we're going to plug in x equal to 0, which gives us 2 times y equals 6. So y must be 3. So 0 plus 6 equals 6 makes the equation true. And for our x-intercept, we're going to find our x-coordinate when all the other variables are 0. So we're going to plug in y equal to 0. So we're going to get negative 3 times x equals 6. So x must be negative 2. So negative 3 times negative 2 is a positive 6. Plus 0 equals 6. So this ordered pair makes the equation true. Therefore, it has to be a point on its graph. So now we've got a point back here at negative 2 on the x-axis, and on the y-axis we've got a point at 3. So we can see we're going to go up 3 and to the right 2. So up 3 to the right 2, up 3 to the right 2. And we can see that these lines are going to intersect somewhere in here. So maybe if I make my line here a bit straighter. So we can see it doesn't really look like it crosses on any of our crosshairs, like our integer values like we had before. But it does look like maybe that x-coordinate here is somewhere between 2 and 3. And so maybe if we made a rough guess, maybe around 2.5. We're going to get some methods to get this more exactly here in just a minute. And our y-coordinate here looks like maybe it's somewhere between 6 and 7. And so maybe, it's really looking like it's almost at 7, so I don't know, maybe we'll just guess and say it's like at 6.75 or something like that. Okay, so again, this is just an approximate solution. We're just trying to make a guess based on our graph. Okay, but it doesn't look like it's crossing like right at 2.7 or 3.7, which is what we had before. Okay, so we're going to get another method to try to figure out where exactly do these lines cross. Okay, and then we're going to kind of come back and check it against what we got here for our approximation and see how close it came to our approximated value.